Hi there, this is Jacob Nash Algebra Lessons. This is Unit 7, Lesson 11, on modeling exponential growth and decay using a formula. Now, I just say a formula because this doesn't necessarily have an exact name, but based on the word problem that you might get, you might want to use this one over the ones that we looked at in Lesson 10. This is for continuous trends, so it's not just like one thing happened, it's going to keep happening, and you're assuming that it will keep happening in that exponential order. So the equation is a subscript t equals ab to the t power. So what that really just means is a to the subscript t, that's just one thing. That is amount over time. And then lowercase a, or sometimes you see it as a with a 0 on it. That's the initial amount. So starting, what did you start with? B is the rate. So are you increasing by 19% or something like that? That's what that means. Remember, growth is if something's increasing, decay is if something's decreasing. T is times elapsed. So sometimes it doesn't have to be years, since it could be any other length, but that's just an example. It could be years since A. And then B, if it's greater than 1, that's growth, and if it's less than 1, that's decay. So that's what that is. Let's look at an example. Okay, this is about the island of Java. The number of people on the island of Java is increasing exponentially. Pretend it is, because it's not necessarily increasing exponentially, but this is just for a problem. In 2019, the population was 148 million. 2020, the population was 150 million. Honestly, since this is only in a year span, it's not the best thing, but this is just what the problem's like. If the trend continues, so since that says continues, that's why we'll use this problem. Exponentially, what will the population be in 2023? So let's put this formula here that we're using. So remember, it's a subscript t equals a b to the t power. Also, this can be a 0, but I think it just looks better like that. And we need to figure out, of all the values we were given, what do they represent? So we have 148 million. We have 151 million. And then we have years here. So we need to know, if we're figuring out what the population will be in a certain year, that means that's what we're going to find. So we're going to say A of t is question mark, because we don't know what that is. Then A, as we see back up here, that is the initial amount. Since the first number was mentioned was 148 million, we would say 148 million. Oh. Well, we're actually just going to use, just for no crazy number's sake, we're going to just use, we'll just say 148, and then we'll add on, remember to add on 6 zeros to whatever answer we get, so that we don't have to go crazy on here. So then we have, we need to know the rate of growth or decay. Well, this actually isn't a very good problem, because it doesn't say that. It just tells you what it was in the next year. So I guess we can technically still find it. This isn't necessarily something you would have to do, but since that's kind of what we have to do. So let's think about the best way to do this. So how has 148 changed to 151 million? We know that if we had 1 to 2, well, actually that's not a very good example. Let's do 8 to 16. We know that would be doubling, so that would be a 2 factor, a 2 rate, and we got that by dividing that by that. So we will need to divide 151 by 148. and we get 1.02. Since that's greater than 1, obviously it's increasing. So that would be our rate. 1.02. So obviously that doesn't even appear to be growing exponentially because it only grew that much. So 1.02. We'll just say that. T, what is T going to be? Well, I said years since A. Well, the starting year was 2019, the ending year is 2023, so that's 4 years. Okay, so now let's plug in our values. So we have T equals 148 times 102, or 1.202 to the fourth power. Let's first simplify that. 1.02 to the fourth power is, we get approximately 1.08. Then 1.08 times 148 is 159.84. We need to add 6 zeros, I said, so really that would be right here, but since we have the 84, we can just eliminate these and just do this. That's not like a skill you would need to know, because obviously that's just something I did so we wouldn't have long numbers. So this would be our answer. So we could just say 159.8 million if you want to be, or well, I guess you could say that, yeah. All right, that's what the population would be. So if we were to put, okay, terrible. It always does that. If we were to put this on the graph, let's see if this even would look exponential. Well, actually, since this is a word problem, that means it's in real. It only could be positive numbers, so I won't draw a complete cross. So I'll just do this. All right, and let's have 100, 200, 300, and then years. Well, actually, that's the wrong thing. That shouldn't be on the x-axis. You might not have to graph it, but just so we can see what it would be like. We can just do this. 1, 2, 3, 4, 5. These are the years. 100, 200, or we can just say 150 actually. So 150, 200. So year 1 was 2019 when we had 151 or 148 million. Year 2 it was 151 million. Then year 4 we skip ahead to 159 million, and we could assume it would be somewhere around here going back. And that doesn't necessarily look like it's exponential, but whatever. So that's it for this video. Thanks for watching, and I'll see you on the next one.